Good evening, everyone. So today we will discuss the section B of internal one data science paper. So hello, I am Ravi Jaiswal, MTech fifth sem student. So let's begin the discussion. So start with first question. So here it is the screenshot. I will dictate it if it is not clearly visible. Briefly outline how to compute dissimilarity between complaints profiles described by normal attributes like jurisdiction, police station, offense category by chapter, asymmetric binary attributes, presence, absence of specific offense elements, criminal force present, property damage present, numeric attributes, estimated loss, incident duration in minutes, term frequency vectors, keywords, phrases extracted from FIR narratives. So we have to discuss methods of compute dissimilarity between complaint profiles using all these four terms. The first one is normal attributes. It includes example of jurisdiction, police station, offense category. Normal nominal means categorical values have no numeric ordering. Dissimilarity between two records is computed using simple matching. If values are same, dissimilarity becomes zero. If values are different dissimilarity becomes one. For multiple nominal attributes, we have calculated that normal attributes equals to d equals to number of mismatches divided by total nominal attributes. The B part is asymmetric binary attributes. Examples: presence, absence of offense elements such as criminal force present and property damage present. Asymmetric binary means presence 1 is more important than absence 0. Use check card distance because it ignores the 0 0 matches. Formula D equals to 1 minus A of A plus B plus C, where A equals to both profiles have 1, B equals to profile 1 is 1, profile 2 is 0, C equals to profile 1 is 0, profile 2 is 1. 0 0 represents absence. Absence is not counted. The third one is numeric attributes. It includes examples of estimated loss in rupees, incident duration. Numerical values require normalization to avoid scale domination, like min max scaling. Common dissimilarity measure is normalized Euclidean distance or Manhattan distance. So then the formula for calculating Manhattan distance is equal to summation of xi minus yi, where I goes from 1 to n. That is the length of the data. If variables are normalized, it is in the range 0 to 1, distances become comparable across attributes. D1 is term frequency vectors from FIR narratives, examples, keywords, important phrases extracted from complaint text. Each document and narrative is converted into a vector of word frequencies. Dissimilarity is computed using cosine distance. So the formula is dot product of this divided by modulo of A into modulo of B. Cosine dissimilarity equals to 1 minus cosine similarity. Alternative Euclidean distance between TF vectors. Final summary of these particular terms. So the first one is attribute type. So in this we how to compute dissimilarity. It signifies nominal signifies simple matching, 0 for match, 1 for mismatch, average over attributes. Asymmetric binary signifies check card distance, ignoring 0 0 matches. Numeric signifies normalized values, use Euclidean or Manhattan distance. Term frequency vector signifies use cosine dissimilarity, which is equals to 1 minus cosine similarity. The second one is we have given these tuples, and we have to which is representing incident duration in minutes, witness present 0 1, exhibits evidence, items count, alleged actor. We have to compute the distances using Euclidean, Manhattan, Minkowski with h equals to 3 and supremum distance. So we have written down the attributes and their differences, which is absolute differences, sorry. So which is 2162, and if we compute the Euclidean distance, so this is the formula for that. For that, here we have four values in each tuple, so the I goes from 1 to 4, and we take under root of the summation of whole squares of these values, so the answer becomes 6.7. In Manhattan distance, the I also goes from 1 to 4, because here, but here we didn't take the square. We take k equals to 1, so it is just the modulus of all the absolute differences between two tuples, so the answer becomes 11. In Minkowski, we take h equals to 3, so instead of 1 by 2 in Euclidean, we have taken here 1 by 3, and the formula remains same. I goes from 1 to 4, and we have to take the cube of the absolute differences of all the terms, so it becomes 1.5. And the last one is suprema distance. We have calculated it by taking the maximum of all the tuple values that we got from the Manhattan distance. So the maximum of 2162 is 6. So 6 will be our answer. One line summary, we can summarize this. Euclidean uses this Manhattan distance is 11. Minkowski is 6.153, and this suprema, which is known as save distance, is 3. The third question is, the median evidence impact score is often a robust indicator for triage, routing to fast track scrutiny versus detailed legal weighting. For massive complaint datasets, propose median approximation methods GK, quantile summarizes, T-digest, reservoir and sampling analyze time and expense complexity, and also suggest heuristics to balance accuracy versus efficiency. So the answer is the median is a stable and noise resistant statistic, but computing it exactly requires storing and sorting all data, which is expensive for massive compliant datasets. Hence, approximation algorithms are used. So the first one is median approximation methods. This question is saying basically for massive data sets, we have the storing and sorting of the data will become complex, obviously. So we have to use approximation algorithms. So the first approximation algorithm is median approximation method. It in this we have a GK, Greenwald Khanna quartile summary. It maintains a compact summary of data using tuples, support online updates, guarantees an e-approximation method, suitable when accuracy must be mathematically bounded. It has a time complexity of big O of log of 1 by e and a query time of big O of 1. Space time complexity is big O of 1 by e. It has a use case accurate median estimation where complaint stream is very large and but memory budget is modest. So the B part is T digest method, in which we have a cluster observations into centroids with controlled error very accurate near the median. Designed for streaming quantiles and works well with skewed distribution. It has a time complexity big of log n, space complexity typically hundreds of centroids, so it becomes big of log k, which is independent of n. It has a use case of large scale triage workflows where precise median around center is required. Third one is reservoir sampling, which is uniform. It maintains a fixed size reservoir size k for streaming data. Median is computed from sample only. Approximate time complexity is it is a constant time complexity. Final median computation for sorting we have required big of log k into k. Space complexity it has a big of k. Use case when streaming is speed is extremely high and approximation median is sufficient, then we will use the reservoir sampling. Now let's move on to the next question. So I have, so this the fourth one is saying we have a simple data sets representing two numerical features, complaint per complaint. The first one is responsive for accused support gain due to infrastructure measures scaled for NLP extension. So we have this given data set. We have a complaint section C1, C2, C3, C4, C5, and we have F1, F2. So and we have a given a query point which is 1.6 and 1.4. So we have to rank all the existing complaints on the basis of distances like Euclidean, Manhattan, Suprema, and cosine similarity. And after that, in B part, we have to normalize each complaint vector to unit length and recompute and again recompute the Euclidean distance. So first one we have to find the distance of each complaint from the query point, that is 1.4 and 1.6. So for C1 we what we will do, we will just do query point represented by C minus all the no the C1 C2 complaints represented by C minus X, which is known as query point. So this is basically calculated the absolute differences between the complaints and a query point. This is also known as a uh, Manhattan distance calculation. Next one is Euclidean distance, in which we will do the summation of squares of query point minus all the complaints, and we will take the under root of that. So accordingly, the C1, C2, and all the distances are getting calculated, and we will rank the closest first. Closest first means the value which has a very less. C1 has less value, then C4, then C3, then C5. Then we will calculate Manhattan distance. So we will rank accordingly. the rank goes like this: C1, C3, C4, C5, C2. And and by the supremum method, the rank goes like this: C1, C3 equals to C4, lesser than C2 equals to C5. Cosine similarity, we will use the dot product of query point into all the complaints divided by modulo of query point into modulo of complaints. The approximate results like this: ranking higher similarity are better. C1 is greater than C4 is greater than C3, C2, and C5. We will normalize complaint vectors to unit length. Normalize each vector. Normalization is just basically a finding a unit vector. And we will, how will we find the unit vector? We will find it, the vector dimension divided by the modulo of it. So we have the approximate normalized value for all the complaints, and we will do the normalization of it. So the normalization come 0.658 and 0.751. So, and the B part also saying that we have to recompute Euclidean distance after normalization. So after normalization, our query point are changes, which is 6.6 and 0.751, and we will do we will apply Euclidean formula between all the complaints and this new query point. So the rank goes C1 less than C2 and like this. So okay, fine. That's all for this particular B section. If you have any query regarding all the concepts I have discussed, so please contact me, and thank you. Let's meet in some other video. Thank you.